One more question?
Yeah, go ahead.
What's Sea Orgs? It's on the line with the fraction dissolved.
Concentration of organic solids. I think that's relic.
It's a relic.
I think that's relic at this point. This program's been around a long time. So for the moment, we'll say it's relic.
Okay.
Yeah, it's interesting. You can see at the very end, the Chester used to be considered a general input, and then with all the attention focused on the Chester due to the shallow water model comparisons, we split it out, you know. Okay. So in any event, and as I mentioned, you have the program that does it. And it's commented, you know, just happened by coincidence, remove split organic phosphorus fractions. So there you go. So it shows you take the dissolved organic phosphorus from the organic, compute the particulate, get the PIP, get the labile refractory, the G3, you know, you have it.
Okay, so the time series that you get from the watershed model are for what years?
There for years from like 1984 to 2000 something.
Okay, so you have to-
14.
Say again?
2014.
14.
Through 2014. So 80 through 2014?
84.
2013.
All right, so if you're running the 10-year record in the 90s, you need to extract just those loads.
That's right.
And does this program do it, or do you have to create your own file?
We provide annual outputs for those years, those 31 years,
Uh-huh.
and COL uses them to process these inputs.
If you want specific years, you'd either have to modify the program a little bit or edit the files.
Okay, so
Easier
this is
modify
going
the
to
program.
provide me with 1990 through 2000,
Well, 1984
oh, through 2000.
to 2014. It processes the whole files. You wanted specific years, it does not look at, you'd have to either modify the program and say, as I'm reading from 1984, don't do anything until you get to 1990.
So if I'm running the water quality model,
Yes.
and the water quality model is running for a 10-year period, how do I specify what 10 years?
You would have to modify this program either to get the 10 years you want, or edit the files, your initial input
Just
files, to get to the
delete
10 years you want.
everything. And they're huge files.
Yes.
Well, actually,
Well-
so the result is 30 files,
No, it's,
one file?
No,
One
it's
file.
30.
oh, 30, the way you do it, 30,
So
sorry.
So
you can
it-
actually.
You could do it that way. I do it, it's one continuous,
Yeah, because
sorry.
yesterday when we did the
Right.
exercise,
Yep.
when we run the.
Oh, it's
10
30 annual files.
Yeah, I was thinking the way I do it, which is
Yeah,
one
yeah,
big
we do
file,
that.
sorry.
And you're getting annual loads, so how are these divided into daily loads?
The daily loads.
They are daily
Daily.
loads.
What?
They are daily loads.
They are daily.
Oh, so you're giving, I'm sorry. It's annual files of daily loads.
That's right.
Well, let's see something. Just because, here we go. I don't know if I can edit this or not, but we'll see if I can take a look at it. There it is. That's what, on the right, there's what Gopal gives me. So what you see is a cell, a year, month, day, and you know what comes out of the watershed model. For that year, month, day, dissolved oxygen concentration, temperature, chlorophyll, flow. There's a PO4, kilogram per day. And over here, these are the cells. So these are the cells that get the loads. What did I say? There were like 4,300 of them, something like that. So that runs down the entire day, or, you know, January 1, 2001, every cell that receives a load. I'm just going to pull down at random, but now we're at apparently 2001, January 4th, at cell 11,052, January 4th. So this is a file of daily loads to each cell that receives a load. And this is for the year, apparently 2001, so we get Eventually, we get 30 of these, and whatever model years we want to simulate, we process them. And let's see.
Could you go into the, if you got a second, or not that important, there is a make file for the point source, correct?
Yeah, but I don't know if I have it here.
Oh, okay, all right,
I don't think I have it here.
all right.
I don't know if it's going to open this or not. I was trying to open the actual water quality model file, and as you can see, I think it's belching. So I'm not going to. I won't tax my editor here. Okay. So that said, I'm going to move on to boundary conditions. It's actually there's not much of a lecture. There's only one slide, but we'll do what we can here. Okay, recall a couple of things. I think I opened up a map file. Yeah, this is first day we looked at a map file for a 30-box model, and this is a map. This is the actual map file for the 50,000 cell bay model. There's a little extra information we get in here, but basically, recall you have a face, a flow direction, these two left boxes for this face 1, and the two right boxes. And in fact, face 1, because this one's a 0, you can see the cell to the left joins a solid boundary. Okay, so, and remember a couple of other things, that the way we identified open boundaries was if we saw 2 zeros, that was an open boundary. And depending, there could be a left or right depending on where the 2 zeros. So you see that this thing is a monster. How many lines? 161,000 lines? Lord have mercy. No, wait a minute, I'm in a different place. Anyway, okay, this file's a monster. So what we have to do is I write a little Fortran program that reads this thing and looks for consecutive zeros and spits those out. Okay, so now we can identify boundary faces. Now, but remember what I said is that these boundary faces are just the order in which they occur going around the perimeter. They don't make, to us, they don't make sense. So particularly the ocean is problematic, but you go to the Susquehanna, then you go to the Chester, then you come out to the ocean, then you go down to the James, and you go to the Rap and the York, and you're back at the Susquehanna, and now you're back. So it's maddening to deal with that. And what you have to do is we have a boundary condition processor. So I think what we'll look at is this one here for a moment. That map file, by the way, is created by an auxiliary program that's attached to the hydrodynamic model. Again, you couldn't possibly type that map file in by hand. It's got to be automated. So what we do here is we'll go over the inputs first. So this is the input for 1 year for a boundary conditions processor. And what we see is James and Appomattox rivers. There are 5 flow faces, open boundary conditions in the James and Appomattox River. And I got the 5 from that little program that I write that goes and spits out, counts out all the zeros. They are encountered 1, 2, 50, 192, and 129. What that means is, if we go around the bay, the boundary conditions in the James and Appomattox will be the first one encountered, the second one encountered, the 51st encountered, the 92nd, and the 129. And I have to get that from that little auxiliary program that I write. Now that we've done that, okay, we can actually put in boundary conditions. And I guess it's not going to let me do that. Let's try this. Yeah, we can do this. So the way this works is we have one of these inputs for each year. And what you see is these are monthly, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 temperature boundaries, 12 salinity boundaries, 12 fixed solids, 12 chlorophyll. Away we go. Once again, we have to, these are based largely on the Chesapeake Bay, well, 50-50, it depends. Some of these come from monitoring stations, Chesapeake Bay program monitoring stations. Some of these come from full-line observations. We won't worry about that at the moment. Once again, though, if you've got, for example, a particulate organic carbon boundary condition, you've got to split that into G1, G2, G3. And, the observations, if you're lucky, it's just going to be particulate organic carbon. So up here, we have specifications as to how to split that into labile and refractory. As I mentioned, for most substances that we load to the bay, we actually load the bay with nitrogen, phosphorus, and carbon. At the fall line, then, the boundary condition is going to be 0. So if you look, for example, at dissolved organic carbon, you can see the boundary conditions are 0 because we load the model. So we don't want to have it flowing across the boundary and being loaded at the same time. On the other hand, for temperature, you see we provide it with values because we don't load temperature. We specify a concentration and let that be carried across the boundary. The same with dissolved oxygen. We specify a concentration and let it be carried across the boundary. Go ahead.
I'm a little confused. So for Susquehanna River, that's also open boundary, but you're using loading file?
Yes.
For carbon, nitrogen, phosphorus.
Then the rest of them are using.
Right. And let's.
Okay, so you said 0. Oh, that's right. Yeah. Everything else is 0. Okay.
There's the Susquehanna River. So the Susquehanna River, there are 5 faces. They are encountered 9, 10, 11, 55, and 94. And again, you have temperature boundaries, but the phosphorus, for example, is 0.
Okay. And in the loading file, there's also a temperature column, right?
There is, but we load 0.
Oh, we put 0 in.
Right.
So what the watershed model didn't simulate temperature?
It does, but we don't use it.
Oh.
And if you ask me why, maybe because I figured if it's observed, why use a model?
Right. Okay.
Yeah, so temperature and oxygen are usually based more on observations. You do get them from the watershed model.
Let's say if I have more than, if I have weekly data, then I just extend.
If you wish to use weekly data, the model will allow it. The model will allow weekly inputs. However, if you have weekly data, you must specify weekly inputs at every boundary. So if you had weekly data at the Susquehanna but not at the James, you've still got to have, yeah.
Okay.
And the other thing is you'd have to do this program is kind of hardwired for monthly. So if you wanted to use this program, you'd have to change it.
Can we go down a little bit on the ocean just to take a look at that?
Yeah.
May have a question, but I'm not sure.
Okay.
Yeah, I do have a question. So, again, at the ocean boundary, we also you also specify a G3 component for the particulates. And again, since there's no G3 there, it's the difference, which is 2% seems to be G3. Okay.
Okay. Now, at the ocean, we're going to talk about the ocean in a couple of regards. Now, the ocean is a different situation than a fall line. We actually have to specify a boundary condition for every substance. We can't rely on an ocean load to get out of having to specify carbon, nitrogen, or phosphorus. So for the ocean, if you look, you'll see that going down this list, every single substance is specified. It has to be. The Bay program has, well, we'll see this in a couple of minutes, or we'll see it instantly. Let's see here. Where's my PowerPoint? Look at this for a minute. There you go. The Bay program has 3 stations across the mouth of the bay. 8.1E. Where's my bay? Well, oh, there's my bay over there. Okay. There's 8.1E, 7.1, and 7.1N. There are 3 monitoring stations. Our boundary is actually more out here, but in the absence of good data at the out there's no monitoring stations, we take these and project them outwards. Okay, that's the way it's done in any event.
Do you modify them when you project them?
I do not.
Okay.
I do not. You know, times change. So a long time ago, we actually put that boundary way, way out there to where it was totally not influenced by the bay. But then when we said, okay, now what's the dissolved organic nitrogen out there, we didn't have any information, you know. Well, there you are, you know. It's a paradox. Now, I think, you know, now I think models like ROMS and such, they actually go out to the shelf, and I guess there's enough. At this point in time, I'm just guessing, but I think there's enough data out there now to where you can make some reasonable approximations of boundary conditions. But that's all history now. Okay, so we have these 3 monitoring stations. What we want to do is, or what we do is, we divide this is a cross-section, if you will, of the mouth of the bay. We're outside the bay, we're looking upstream. So we divide the bay into a couple of regions, and the regions are sort of, we divide the bay into a couple of regions. So we have like surface, middle, or left, middle, and right surface. We have down here, we have what I call the pycnocline, and I guess we have 1, 2, 3 pycnoclines, and then we have this deep layer. And, you know, so for example, this really deep layer, we use the data from CB 7.4. For these 2, the surface and the pycnocline, we use CB 7.4N, and so on. And what it looks like, coming back to here, yeah, you see, so for example, north shelf surface mixed layer. So this is that surface, and this is the northernmost of those 3 surface layers. And here you see, now you got a lot of faces. You got 50 of them, because that's it's not a little river anymore. It's wide, and it's 19 layers deep, or as much as 19. And once again, once you have that, you're back again to, you know, as I said, you go to the monitoring data for station CB 7.4 and you specify the boundary conditions. And inevitably, they didn't go out 1 month and you have to interpolate, or they got a bad sample, and you know, you're going to wind up doing a lot of hand. If you do this from scratch, you're going to wind up doing a lot of stuff by hand, but once you have it done, it's done. And you know, you can see, so there's the south shelf surface mixed layer, go all the way down to, what's that, the deep mixed layer. So, but basically so your job really is to put together this file. if you were doing the Chesapeake Bay, because, and you let the program that, and the program's in your, what is it, bcond_prep, this one, _G3 organics. That program will take the sort of rational inputs that you've created. Here's the Susquehanna River, here's the ocean, and it will use that information as to what order they're encountered, and it will spit out a boundary conditions file, which probably looks like this. There's a boundary conditions file. So there are 243 open boundaries, and there's the temperature on day 0. There's the temperature at all 243 of them. Next one, there's the salinity at 243 boundary conditions. So you have the processor and away you go. Okay. Questions about boundary conditions?
Just on the spot, there's, I don't know, number of lines down, there's a boundary condition of 4 parts per thousand.
For salinity, yeah.
Yeah, so could that be a typo?
It's probably the Chesapeake and Delaware
Oh.
C and D can have.
So you had the C and D in there, okay.
Yeah.
All right, thank you. Huh.
Okay, so be it. Close that thing down, close that thing down, close that thing down. All right, so remaining, the last one we're going to go over today is the heat exchange hex processor.